Welcome to ECE 302. This is lecture 5.5 on conditional expectation. I'm Professor Stanley Chan. If you recall our last lecture, we introduced two very important concepts. One is called the conditional PMF, the other one is called the conditional PDF. They are the conditional distributions of a pair of random variables. Let me try to review what is the definition of this conditional PMF and the conditional PDF. The conditional PMF is defined in this way. On the left-hand side of this equation, we have this distribution of x given y. What it means is that if you have a pair of random variables, we assume that the y variable is fixed at certain value. And then we look at what is the distribution of x. And therefore, on the right-hand side of this equation, you can see that it is defined as the ratio between the intersection and also the marginal PMF. Thus, we have also discussed the meaning, which is really the event that x equals to x and y equals to y divided by the probability that y equals to y. And so what it means pictorially is that you have two events and then you're looking at the intersection over one of the two sets. So this is the definition of the conditional PMF, and similarly you can define the conditional PDF for continuous random variables. So the conditional PDF of x given y is defined by this quantity here, which is again a ratio now between the joint PDF over the marginal PDF of y. So if you're given a conditional PMF or conditional PDF, then you can calculate the probability such that y equals to a value y, and then what is the probability that x belongs to a certain set A. Okay, so for example, the probability that x is living in a set A, given that y equals to a y, that you can just integrate your PDF of x given y dx over all the possible values of x inside this set A. Now, note that in this case, this probability will be a function of y, and that is expected because you're restricting your y to a specific value, and therefore when you do the integration, all the x will be gone, but you will still have y left. Okay, so this is really the meaning of a conditional PMF and in the conditional PDF. In order to calculate the probability, you plug in the conditional PDF, and then you calculate the probability. So in this lecture, we're going to learn about something very, very similar to this idea, where instead of just calculating the probability, we try to put an x over here. Now, what is it? Well, you're evaluating this conditional PDF and then multiply with the x. So this is really like taking an expectation, and we call this as the conditional expectation. Okay, so let me go over the outline of this lecture, and then I'm going to define what do I mean by conditional expectation. We're now in the fourth section of this chapter, which is on conditional expectation. This is highly correlated with our previous lecture on conditional distribution, which can be traced back to joint expectation as well as joint PDM and PMF and also CDS. In this lecture, we're going to learn about three things. One is the conditional expectation. What is the definition? What does it mean? Two is that we're going to learn a tool, which is a decomposition tool. It's called the law of total expectation. And then we're going to talk about several examples to make sure that you understand the idea. So what is the definition of a conditional expectation? Let me try to make sure that you understand the idea. Whenever you talk about expectation, you need to specify the PDF or the PMF. In a normal setting, when you have a random variable, what you do is that you will take the expectation of x, this is going to equal to the integration of fx of x dx, and then you multiply with the x. So if you try to calculate the conditional expectation, which is the expectation of x conditioned on the fact that the other variable y is restricted to certain value, then we should expect to see the similar formula as in the ordinary case. What will become different is that instead of using the this PDF of x, we're going to replace it by the PDF of x given y, where y is restricted at a specific value. Okay, so this is called the expectation, and here is called the conditional expectation. So you may wonder, if now I have x here, and then I have this fx given y, what should be the integration? Well, the integration is still on dx, and you're still integrating over the entire set omega. So the only difference going from the traditional distribution, the traditional expectation, to this new thing called a conditional expectation is to replace this PDF by the conditional PDF. And if you understand this idea, you will understand what conditional expectation means. It's nothing more complicated than replacing the PDF with the conditional PDF. So of course, this is not the same as expectation of x. It's called the expectation of x given that y equals to y. All right. So now, if you have a continuous random variable, then here is the definition. If you have a discrete random variable, just replace the integration with the summation. Then you'll be able to get a conditional expectation for x given y equals to y. So I hope you can see the definition, what they mean to have this notation of expectation of x given y equals to small y. It really means that your y variable is fixed at certain deterministic quantity. So there are multiple states of y, but you're looking at a particular state. So in other words, if you have a diagram here, y can take many possible states, but you're looking at this particular state. So this is your event y equals to y, and within the set you're looking at this intersection where x equals to certain values and y equals to this y. And therefore, when you take the expectation, you're taking the expectation over this smaller set, not the entire sample space. And that's why you need to replace this ordinary PDF by this conditional PDF. So exactly what is conditional expectation? This notation, expectation of y given x given y equals to y, is the expectation using this conditional PDF. If you can remember this single most important idea, you'll be able to do a lot of these conditional expectation calculations. Just do not be confused with fx and fx given y. Okay, here is the ordinary PDF, and here is the conditional PDF. If you try to integrate this, you will get a number. If you try to integrate this, you will get a function in y. That is still a number, but this number depends on y. So now, if today you have this y equals to 5, then it will be a function of this number of 5. Okay, so it is no longer just a fixed quantity. If you do this calculation, it will be a fixed quantity. It will be just the mean of this random variable. Thus, when you try to take the expectation, you are going to take the expectation of this random variable, x given y. And so now, imagine that you could go to this sample space. You have x and y. This is y y equals to 1, this is y equals to 2, this is y equals to 3, and then you have certain events over here. Then you ask what is the conditional expectation of x given that y is 1. Then you're really looking at this as your base, and then you're looking at this event inside the green box as the expectation. And so if you choose 1, that would be the integration area. If you choose y equals to 2, then it would be a different story. You need to look at this 2, and then you look at the intersection over here. That would be the expectation, conditional expectation of x given y when you're looking at 2. And therefore, as your y changes, your output value will change. That's very different from the first case. The first case says that you have this PDF, just integrate over the entire PDF, and you will get a deterministic number, and that's just one number. Here it will be a function of the whatever y that you specify. Now, as we are talking about this decomposition, you can see here in this diagram, I have multiple states of y. The following theorem will become very useful. This is called the law of total expectation. What it means is that you have the conditional expectation, which is a function of the y. And then you want to calculate the overall expectation. It turns out that this overall expectation can be written as the conditional expectation multiplied with the probability of a particular state of y. You sum over all the possible states. So you may wonder why this can ever be useful. Here is a diagram that shows you what is going on. Let's say I have a sample space. This is my sample space omega, and I am partitioning it into 4 subsets. Okay, by partition I mean that they are disjoint, and then the union of them will form the entire sample space. So you can calculate the conditional expectation of x given y equals to a particular value of y. So for example, here I will have the conditional expectation of x given y equals to small y4. So that would be the area that I'm looking at, and then the base that you are considering would be this. So after you calculated this, you will have this conditional expectation of y equals to y. Now, however, we know that this y is a random variable, and so if you go back to here, we know that this y, this entire expectation will be a function of y. So if my y changes, my expectation will also change. And therefore, we need to know what is the probability of getting this particular state, y equals to y4. And let's say here is your PDF of the y. Y is given by here. You have 4 states, and then y4 has this probability. And therefore, you need to multiply this with this number. So you have this probability y of y4. You multiply with this number, and then you sum over all the other cases. Then you will be able to get this entire region of expectation mix. The law of total expectation is really the statement about this. It says that if you want to compute the expectation mix, you need to compute the individual conditional expectations first, and then you multiply each one by its corresponding likelihood, which is the PDF of y. You integrate or you sum over all the possible values of y. Then you'll be able to retrieve the expectation mix. So what is the law of total expectation? It is a decomposition rule. It is a decomposition because you decompose an event into smaller events. And certainly, I think you will remember what we have learned back in chapter 2 when we talk about conditional probabilities. We say that the law of total probability can be very useful because it decomposes a big event into smaller events. So this law of total expectation is along the same line of thinking. All right, so how do we prove this law of total expectation? It actually turns out to be fairly easy to prove. So here is the expectation of x, which is the ultimate thing that we want. I can define it as this, which is the summation of x times px. So now we look at this. This has nothing about y, and so we're going to introduce something about y. So let me keep the x outside. Let me keep the x here. But I want to write this px as a py. Okay, so let's say I have px y of x and y. Okay, if I start with the joint distribution, what can I do in order to get px? Well, I can sum over all the y's. All right, so now you can see that this is the same as this sum over all the possible y's. This is the marginal PMF. This is the joint PMF. And then we can look at this summation. This is a double summation, so you have sum over x and sum over y. So sum over x go to here, sum over y go to here. Your x will remain here. How about this term? This term is the joint PMF. This joint PMF is the same as the conditional PMF, px given y, times py over y. This is the definition of the conditional PMF, which is also follows from the definition of conditional probability. So you put this into the equation, then you will see that this equation will go to here, where you have a double summation of x times this conditional PMF, and then there is the prior PMF. And then what? Well, and then we can try to look at the terms. How about we look at how about we switch the order of the summation first? Okay, so let's take the summation over x first. All right, so now you have x and then px given y of x given y, and then there is a py of y here. Now this term, I hope you can recognize, this is a summation of x times this conditional PMF. So what is it? Well, this is a conditional expectation of x given y equals to small y. This is because of the definition of this conditional PMF. Okay, conditional PMF and also the conditional expectation. Now, when you try to take this summation here, well, what is it? So if you rewrite it, I will have this equation. This equation says that going through all these steps, the final result would be a summation of individual conditional expectations on y times the PMF of y, sum over all the possible cases of y. I will be able to get back your original expectation of x. So this proves the law of total expectation. So at this point, I think you may start to realize, what do I really mean by this conditional expectation of x given y equals to small y? This thing, conditional expectation of x given y equals to y, it is a deterministic function in y. It's a deterministic function in y. What does it mean? Well, it has to be a function in y, because if I change the value of y, this quantity here will change. However, the change would be a deterministic change, because there is no more randomness about the y. Y is just fixed at that particular state. So if you have 5 states of y, once you have picked at this state, you will be there. You will fix at that particular state. Certainly, there are probability of getting that state, but you don't care. You're just looking at the conditional expectation at this particular state. I'm not asking you about the expectation over the entire range of the y. I'm just looking at one particular y. So that is the meaning of this conditional expectation at one y. Now, if you do not put this notion of y equals to y, okay, if you do not put it over there, then what is it? Well, it will become a random variable y. It's no longer just a specific value of y. It will become a random variable y. This is called random variable. Why? Because you have multiple states to choose from. You can choose this, you can choose that, you can choose that. And so if you do not specify anything, which y you are landing on, then you will be able to get a random quantity. So this is random. This is deterministic. It is a random quantity because you have a random y. And therefore, if you no matter which y you pick, it has to be a random variable. And therefore, if you say that I compute this would be a function of y. Okay, this would be a function of small y. So there's nothing random here, but there is something random over there. And therefore, if you want to say, I want to get a deterministic quantity, I want to get rid of the y, then you can say, I want to put an expectation of the y's. Okay, now if you put an expectation of the y's, that will stay as fy. But if you take the expectation of this, you need to integrate your fy over all the possible values of y and then dy. Okay. Now, of course, this f could be a little bit confusing here, so let me use another notation, how about we call it h. Okay, so then you have hy and then py of y, and this and we call it the PDF. Okay, so from minus infinity to infinity. This expectation of y has nothing to do with this one because you have already fixed at that value. Okay, how about here? Here you have a random variable y, and if you take expectation, you need to integrate. So that's the difference between this quantity here and that quantity here. This is a random quantity, this is a deterministic quantity. And therefore, the law of total expectation can take a compact form or an alternative form. The alternative form says that if I compute this thing, which is the later quantity here, it is a random variable of y. If you want to take the expectation of y outside, you will be able to get a deterministic quantity, and that deterministic quantity is exactly the expectation of x. So you may wonder, oh, this is extremely confusing. It's actually not that confusing if you follow the proof carefully. Let's start with this expectation of x. It is defined as the individual expectation on a particular value of y, and then you take the sum. You take the sum over all the possible values of y. This is because you have multiple states of y, and then I need to pick a particular one. So it could be y equals to y1, y2, and y3. There are certain probabilities of landing on one of these impulses. So I need to sum over all the possible cases in order to get to this expectation of x. This is by the law of total expectation. And now, what is this conditional expectation? This conditional expectation, as I said, it will be, since you are fixing yourself at this small y, is literally just a function of y. Let me just call it h of y. It's a function of y. And then, when you try to take the summation times the probability, essentially you are taking the what? You're essentially taking the expectation of this random variable h of y. And therefore, if you write out the detail here, this h of y, you go back, this h of y is the expectation of x given y, x given y. This is a random variable, and therefore you can take the expectation of y outside to get a deterministic quantity. That is this expectation of x. And therefore, if you want to calculate this expectation of x, you can write this double loop of expectations, one on y outside, one on x over y. So that will calculate the expectation of x. All right, so let's go through a few examples to make sure that we understand the idea. The first example is as follows. Suppose there are two classes of cars, and let x be the speed and c be the class. If you're C1, then you have one Gaussian distribution with mean mu1 and variance sigma square. If you're class 2, it is another Gaussian with mu2 and sigma 2 square. The probability of getting a class 1 is p. The probability of getting class 2 is 1 minus p. So imagine that you see the car on a freeway. We ask, what is the average speed of a car? Now, this diagram will illustrate what the problem asks. You have a Gaussian distribution for car 1, Gaussian distribution for car number 2. You go to the freeway, you look at the car. That could be this type of car or that type of car. You get one of the two types of cars at probability p 1 minus p. And if you get this one, you will have this mean and that variance. You look at this type of car, you have this mean and that variance. What is the average speed overall? If you just look at one car, what is the average speed? So this problem can be calculated using the conditional expectations as follows. We can define the conditional PDF of each individual case. So what is it? Well, the first one is a Gaussian. Okay, the Gaussian of mu1 and sigma 1. And so this is really 1 over root 2 pi sigma 1 square e minus x minus mu1 square divided by 2 sigma 1 square. The other class is Gaussian mu2 and sigma 2 square, and it will be the same formula but just replace all the mean and variance by the specific class. So this should be clear because you need to land on a particular class in order to define the Gaussian. Now, once you're conditioned on C, we can calculate the expectation. There are two expectations here. The first expectation is the expectation of x given that C equals to class 1. So what is this expectation? This expectation, you can see that here is the expectation x given C equals to 1. So this is really the expectation of your Gaussian of mu1 and sigma 1 square. Okay, I just need to really put in this PDF into this calculation, then I will be able to get the expectation. And now you're looking at this Gaussian, so it will be mu1. Okay, now if you really want the formula, this formula will be an integration of x, and then you put in this PDF here, which is 1 over root 2 pi sigma 1 square e minus x minus mu1 square divided by 2 sigma 1 square dx. Okay, so if you plug in this calculation, you will be able to find mu1. The other case, of course, it will be Gaussian, and then mu2, and then sigma 2 square, and then you'll be able to get mu2. And therefore, what is the overall expectation? The overall expectation is, of course, mu1 times whatever probability that you will have for class 1. So that will give you p, and then mu2 times the probability of getting class number 2. If you want to have a clearer formula, this is mu1. Mu1 is the expectation of x given c equals to 1, and then you have p of c that goes to 1, and then expectation of x given that c equals to 2 times p of c equals to 2. Okay, so if you plug in all the numbers, you will be able to get to this expectation. Let's try another example. In this example, I have a pair of random variables with a joint PMF given by this table. I want to find these two expectations. Expectation of x given y and x given y at these two particular states. Okay, so what are the how are we going to solve this problem? Well, the first thing we need to solve is to first come up with the conditional PDFs. The conditional PDFs for this case is given by this notation, is pxy given that y equals to 10 to the power 2. So here you have 10 to the power 2, and then you have all these numbers. And then we know how to calculate this conditional PMF from the table, because this is the joint. The conditional PMF x given y is just p x y xy divided by py of y. So you can just plug this in, and then you'll be able to get this 1 over 2, 1 over 3, 1 over 6 by just calculating this 1 over 12 5 over 15, 18, 5 over 36, divide by over the sum of all these three numbers. You'll be able to get to this conditional PMF. Same for this conditional PMF. Now, once you can get this conditional PMFs, we ask what is the conditional expectation. So let's say we're using this conditional PMF, and then the probabilities are these values. So in order to calculate this conditional expectation, what we can do is to go back to this table and see what are the possible values of x that would land on these three probability values. So in this case, it would be 0 0.01, 0 0.1, and 1 for these three cases. If you do the calculation, it will show that it is 123 divided by 600. When y is 10 to the power 4, then what would be the values? Well, when y is 10 to the power 4, you're looking at this set of numbers. So then you will have 1, and then you have 10, and then you have 100. You do the calculation, you'll be able to get to this number. So finally, if we want to find the expectation of x using the law of total expectation, how are we going to do that? Well, we need to have this conditional expectation of y equals to 10, 2, and conditional expectation of y equals to 10, 4. We need to put in a number, and this number here is py, where y is 10, 2. This is py, where y is 10, 4. So these are the two numbers. However, what is this probability? This probability can be easily found by taking the summation over here. Py 10, 4 will be equal to the sum of these numbers, and then py 10, 2 will be the sum of all these numbers. Okay, so if you do it correctly, you get 5 over 6 and 1 over 6. So you put in 5 over 6, you put in 1 over 6, you'll be able to get to this final answer, which is the expectation of x. If you don't believe me, you can go back and try to find the marginal PMF of x by taking the column sums. And then you'll be able to see this calculation. So finally, let's look at the third example. In this third example, we are looking at a pair of random variables, x and y, and that x is Gaussian distributed in mu and sigma square, and then the other random variable y has a conditional distribution, y given x, which is x and x squared. So this is a little bit complicated example where you need to specify y conditional on x, and then the mean depends on x, and the variance also depends on x. Now our goal is to find the expectation of y. So before we do anything, we can write down the equations for these two cases. The first case is just the ordinary PDF for x, and that is easy. That's just the Gaussian. That comes from here. The other distribution here, it would be y given x, so it has to be the conditional distribution of y given x. So we have f of y given x, and then you have this number here. That would be 1 over root of 2 pi x squared. Where does this x squared come from? The x squared comes from the variance. And also this y minus x, so that's y minus x. So you have this x over here and the x squared. So you can see that this conditional PDF is y given x. Of course, this is different from the usual notation that we have is x given 1. But that's just a small thing. Now, the very confusing part of this equation is that you have both y and x. Okay, you have x here, you have x here. Whenever you see the problem like this, you need to understand which number is a deterministic quantity, is a fixed quantity. Which number is a variable that you need to apply the integration. Here, the number that is fixed is the x. So one way to think about this is that you can replace all the x by whatever thing that you want. Okay, so it could be 1 over root 2 pi, if you like an apple, you put an apple square, e minus y minus apple square divided by 2 times apple square. If you write it in this way, then you will make sure that you know when you try to do the integration, it will be integration with respect to y. All right. So otherwise, when you try to put everything together, you're confused about the varying part and also the invariant part. You will mess up a lot of calculations. So now, after we have written down this pair of equations, we ask how can we move forward to calculate the actual thing we want. We can calculate the conditional expectation of x given x. So what is this? This has to be the integration of y of f of y given x dy. Why is this? Well, this is just the definition. You have integration with respect to y, and then here is the conditional PDF of y given x. Now, this is very important to write it correct, otherwise your following calculations will all be wrong. This has to be the conditional PDF because you're looking at the conditional expectation. Now, we ask, what is this conditional PDF? This conditional PDF we have calculated. It is this thing, or if you prefer, it's just the same with by replacing the x with the apple. This is it. It is an expectation of this Gaussian. Why? Because you can plug it in this quantity here, which is 1 over root 2 pi apple square e minus y minus apple square divided by 2 apple square. So when you try to do this integration with respect to y, what do you get? Well, you're trying to find the mean of this Gaussian distribution. Of course, the variance changes with the mean, but nevertheless, it is still a Gaussian distribution. And you're finding the mean of this Gaussian distribution. So what is the mean? The mean will be the apple, okay? And so now what is the apple? The apple is your x, so you have x that comes out from this calculation. So once we have found the conditional expectation, to find the expectation of y, it will just be the expectation of the y given x equals to small x. And then what? And then you have fx of x dx. So this is your x. Okay, we have found from the previous calculation. So this is x. And then what is this? This is just another Gaussian 2 pi sigma square e minus x minus mu square divided by 2 sigma square. So when you're trying to integrate this entire thing, you're trying to find the mean of this Gaussian random variable. And so what is the value? This one is mu. Okay, and so we found that after all these calculations, the expectation of y is just mu. So I hope that this example has given you some ideas of what do we really mean by conditional expectation and also the ordinary expectation, and how do we link the two. So to summarize, I want to just mention a few points. One is the expectation of x given y equals to small y. Okay, this is the integration of f x given y and dx. And don't forget there's an x over here. Whatever expectation you're taking at, you need to fit in the correct PDF. The other one that is important to know is this outer expectation of x. This is the integration of expectation of x given y equals to y. Okay, and then you have fy of y dy. This is called the law of total expectation. It says that I'm going to first compute the individual conditional expectations, and then I'm going to multiply with the probability of the y, and then I integrate. Then I will be able to get this overall expectation. So I hope you can understand the importance of these two examples and these two statements. And I hope through the examples that we have discussed, you can have a better understanding of how we apply these results. In data science, and these results are extremely useful, they're extremely common. So at this point, I will really encourage you to think deeper about the meaning of these two equations, and I will encourage you to try our homework. If you have any question, I will really encourage you to ask at this point to make sure that we really get the idea. So this is the end of today's lecture. As I said, please feel free to post your questions on Piazza or send us an email. We'll be very, very helpful, happy to help you on any questions that you have. So thank you very much.